In this section, we will study about the inverse Laplace transform. Inverse Laplace transform is defined in this way. The time domain expression are given 1 over 2 pi j. Okay. 1 over 2 pi j, and integration range sigma infinity and minus j infinity and hs. Basis function is st and integration over ds. This one is definition for the inverse Laplace transform. To figure out the inverse Laplace transform, we need to know these integration results. We will study about that one. Here shows the first example. We would like to find out the inverse Laplace transform over hs of this one with a given reasonable convergence is like that. Real part of s is greater than minus omega 0. Here shows that the minus omega 0 is the pole. The single pole are given here, and the reasonable convergence is right side of that pole. Okay. To find out the inverse Laplace transform, we would like to close the contour integral, this one first. hs times e to the st and ds, and on the this contour c. Closed contour c is composed of two different segments. This closed contour consisted one straight line segment. This line segment, if we follow the counterclockwise direction, is starting from the sigma minus infinity to sigma plus infinity. In these directions, we have to take integration. That's this part. So this one shows that the straight line segment part. The second segment is a C1. This C1 is a circular one. So it has a radius is r. It is changing from the half circle. So starting from right angle pi over 2 and 3 pi over 2. That's the finished point. So this segment corresponding the circular part. To figure out this integration, we need to investigate this is C1 integration, this segment integration. To find out this segment integration, we would like to let the s is equals to r e to j zeta plus sigma. If we follow this path, then s should be given like that. It should follow the circular the path. So if s changing along this path, then it is expressed in this way. R and sigma should be fixed. This point is sigma. Okay, this one. There is a single variable exists here. It's a theta. That's why we can write this ds is given as rj zeta, r e to the j zeta, d zeta. Okay. Because if we follow this curve, only theta is the variable, r and sigma is constant. That's why we can write ds is rj e to j zeta and d zeta. If we replace the ds and s in these integrations, then it is given like that: r e to j zeta plus sigma, and this e to the st is also expressed e to the r e j zeta t plus e to the sigma t. At here, we need to focus on this value. This one we need to consider. From here, theta will changing from pi over 2 to the 3 pi over 2. Okay, and if we take r is very big number approach to the infinity, then real part of this one, it means that the theta is only exists in between here. Okay, so when we take the cosine theta, then this number is obviously negative infinity if r goes to infinity. Then if t is positive, then it is minus infinity. If it is minus infinity, this goes to the 0. Exponential minus infinity should be 0. So that's why this integration is 0. So this is precondition. The t should be positive. Then this segment integration is 0. So this part will be vanished out. Then this closed contour integral are equals to this linear segment integration. Okay, this segment integration are equals to this closed contour path integral. But the closed contour path integral can be found by residue theory. Residue can be found by use of these equations. And here the unit step function is added because of these conditions. This means right-sided signal. Right-sided signal. To be a right-sided signal, we need to attach the unit step function. The HS is singular at minus omega 0. So to find out the residue value at that point, we can calculate this one. So S approach minus omega 0. So S plus omega 0 times HS gives omega 0. Okay, that's this one. And S approach minus omega, then e to the st becomes e to the minus omega 0 t. And 2 pi j are added here, and unit step is given here. Then we can find out the inverse Laplace transform. This is definition for the inverse Laplace transform. So by replacing this integration from this residue value, then we can find out omega given like that. And the second example shown here is the same shapes. The HS is the same, but the region of convergence is opposite side. So in this case is left side of this value. Then it is given like that. HS is omega 0 of S plus omega 0. It's the same as the previous example. So the HS is the same, but the region of convergence is different. Now consider this closed path integration. Here, the closed path also should follow the counterclockwise direction in these directions and these directions. So the contour consisted of two different segments. One is a straight line starting from the sigma plus j omega, and follow the counterclockwise direction and then finished at the sigma minus j omega. So the integration direction should be this direction to follow the counterclockwise. And the another segment is this C2. C2 is a circular one, so we should follow counterclockwise direction in this integration. Consider this integration first. C2 will change from minus pi over 2 to pi over 2. The angle is changing from in this way. If we follow this path, the S should be equal this value like that. S is given R e to j theta plus sigma. As we talk about the previous example, it's the same. If S follow this curve C2, then S will be changed by only theta value. At here, the R and sigma is given one. It doesn't change, only theta changed. So ds are given rj e to theta times d theta is ds. So we would like to replace this one with s is given r e to j theta plus sigma, and also r. At this moment, I replace the real part of that one, e to j theta. Okay, from here, e to j theta is r times cosine theta is this one, and j r sine theta t is here, and e to sigma t is here. But the issue is this one. R goes to the infinity, then this part will approach to the 0 if t is a left side one. So this one is definition of the left-sided signal. Left-sided signal means u minus t. Signal only exists t is less than 0. Okay, that's this one. At this moment, the theta changing from minus pi over 2 to the pi over 2. So we can rewrite this closed contour integral here, but the C2 segment, as we talk about here, it's vanish out. So this integration goes to 0. Then we can change the integration direction and add the minus signs on here. So these integration are given minus over sigma minus a infinity to plus a infinity. And this closed contour integral can be done by use of residue theory, 2 pi times the residue. At this moment, it has a single residue at the minus omega 0. So we can calculate the residue from here. This one added because of the left-sided signal. So if s approaches to minus omega 0, this part becomes omega 0, and e to the st is e to the s minus omega 0 t and minus t. Okay, but this one corresponding to minus over integral of this value. Then the inverse Laplace transform is defined in this way. Then replacing this integral on here, then that will give minus omega 0 and e to the minus omega t and minus t. This is the inverse Laplace transform. By use of the residue, we accomplish the inverse Laplace transform. Now let's just summarize that the inverse Laplace transform of any xs value. If Laplace transform is defined the region of convergence as like this way, real part of s is greater than maximum value of a real pole, then the signal is right-sided. It means that the region of convergence is defined like this way, right side of this one. So the maximum sigma r is this one. So sigma should be right-sided value of that one. That's this region of convergence type. Then the signal is a right-sided one, and the integration angle is negative. It means that when we take the integration over the contour shapes looks like this one. Okay, so right counterclockwise is this directions. So in this contour, it means that the circular contour integrations, we take the theta changing from pi over 2 to the 3 pi over 2. In that case, the r is the radius of that one, and theta is this one. So theta changing from pi over 2 to the 3 pi over 2. Then this part becomes the negative value. It means that the real part of r e to the j theta, that's this real part, is negative. So if t is positive, it means that the r e to the j theta times t goes to the minus infinity if r move to infinity. So this is the vanishing conditions of C1 segment integrations. So this segment integration approach to the 0 in these conditions. And the second region of convergence looks like this one. Real part s is less than minimum value of the real poles. Then the signal is left-sided signal. It means like this one. Here is the sigma left, and region of convergence are defined in this way. Okay, then the integration contour should be looks like this one. Okay, the linear segment from high top to the bottom, and the C2 segment looks like this one. In the C2 segment, the angle will change from minus pi over 2 and follow this path and finish at the pi over 2. So that is the reason. If S exists on this contour path, we follow this path, then real part of r e to the j zeta, that's this one, is positive infinity. It should be positive. Then to vanish this the path integral, we need to take t is less than 0. It means that r e to j zeta times t should approach to minus infinity as r goes to infinity. If r approach to infinity, then r e to the j zeta t should approach minus infinity. That's why this integration is vanished out. So we can take a inverse Laplace transform based on this integration. Find the correct inverse Laplace transform. We need to consider reasonable convergence. The first case, the reasonable convergence shapes looks like this one. The maximum real pole is defined as this one, and all the poles should be exist the left side of this sigma. So pole should be exist the left side of here, and the reasonable convergence defined like that. So real part of sigma, real part of s, real part of s should be greater than this one. In that case, that is a right-sided sigma. The means of this one, all poles should be the left side of this line. Okay, that's the sigma. And in that case, we need to calculate all the residue value of each poles. Each pole's residue value should be calculated at each pole point. Then we can find out the right-sided sigma. And the other case, as we have done in the example 2, the reasonable convergence is defined. Here is a minimum value of the sigma value, the pole value, and all the other poles exist right side of this line, and the reasonable convergence defined in this area. In that case, it is a left-sided signals. To find out this integration, we need to take a contour like this way. So to encircle all the poles of the right side of that one, then we need to calculate each residue values on each pole in each poles. Okay. Now consider the inverse Laplace transform of rational function. Rational function is defined like this way. Xs is defined the numerator divided by denominator, but both the numerator and denominator, it can be expressed as a sum of polynomial. The degree of numerator polynomial is m, and the degree of denominator polynomial is n. We would like to assume that the n is greater than m. In that cases, we would like to calculate the inverse Laplace transform. Here is an example. The first one is xs defined s plus 1 and s minus 1 over 1. And the reasonable convergence are defined. A real part of s is greater than 1. We can plot the reasonable convergence over here. So there is a two pole. One is a positive one, plus 1. Okay, this is 1. And the other one is minus 1. We have two pole. Okay. And the reasonable convergence are defined in the right side of this one. So reasonable convergence are defined in this area. So sigma should be greater than 1. Okay. So we would like to find out the inverse Laplace transform of this one. Here is a two poles that exist. So we need to take an integration path like this way. We would like to take integration counterclockwise and follow circular and this one. So we take this contour integrations. Then this C1 segment integration will goes to 0. Then we can find out the sigma minus j infinity to sigma plus j infinity. That will give an inverse Laplace transform. So to find out the inverse Laplace transform, we can use the residue value. So at this moment, it's a right-sided one because there's reasonable convergence. First, we would like to find out that this value's residue first. That's the shown here. S approach to the 1. Okay, this is 1 point. And we calculate s minus 1 times xs times e to the st. We would like to calculate this one. Then if we multiply these two things, then 1 over s plus 1 is remain, and we replace s equals to 1. So this one becomes 1.5. That's this part. And s is 1. Okay, so e to the st. But this one shows that the right-sided one, e to the t times ut. Okay, the next one is we approaching s is minus 1. We calculate the residue value at minus 1. Then we can find out this one. So right here, if we multiply s plus 1, then this one will cancel out and we approach to -1. So in this case, -2, 1 over -2, and e to the minus t. So -1.5 and e to the minus t, and this one is the right-sided one. So the inverse Laplace transform of this one are given like this way in the region of convergence defined in such a way. The second example, the Laplace transform has the same shape, but the region of convergence is not like that. In this case, region of convergence is given like this way. This is a left-sided pole, right-sided pole is this one. And in this case, the region of convergence are defined less than -1. So region of convergence are defined in this area. So real part of the S should be less than -1. So this one means that the left side is signal. So we need to take integration path like this way. This one is a linear segment, and the right-sided one. This circle should, you know that C2 and this linear segment should enclose both of the pole. Okay. Then this one will starting integration from sigma plus j omega to down sigma plus minus j omega. You need to careful the path directions. We have the integration this direction. We have to follow this path. In this case, it's the same that the residue has a 2 point. One is a -1, the other one is a +1. So firstly, we have to integrate the sigma plus j omega to the sigma minus j omega. So the direction is a top to bottom. That's why minus sign is added here. And we would like to calculate the residue value at 1. As approach to 1, then we need to calculate this one. So minus is added here because of this integration direction. And if we multiply s -1, then this one will cancel out, and we replace s equals to 1, then it is 1.5, and the t is 1 e to the t, and it's a left-sided signal, so u minus t should be multiplied. So this one corresponding the residue value of at s equals 1. To find out the s equal -1 residue, we have to approach s to the -1 and multiply this value. Then this one cancel out, and if we replace s with the -1, then it will give 1 over -2. But because of this the opposite direction integration, then minus will cancel out, so this becomes the positive value. So this negative becomes the positive and 1.5, and we approach the s to the -1, so e to the minus t, and it's a left-sided one. So we have inverse Laplace transform of this one by use of residue theory. The next example is the same Laplace transform with a different region of convergence. At this moment, it is the narrow strip of region of convergence. So region of convergence is defined. We have 2 poles. One is a -1, and the other one is 1. But the region of convergence at this moment is a right side of this one, and also left side of this one. So sigma should be greater than -1 and less than 1. Okay. In this case, we have 2 different directions. In this boundary is a right-sided signal. Okay. So at the -1 pole is a right-sided one. So and the +1 pole is a left-sided one. Okay. We have 2 poles with different directions. Okay. So calculate this one first. This one corresponding to left-sided signal. So we have to take integration direction is opposite in left-sided one. So -1 is added here as approach to the 1, and s -1 times xs times e to the st. You know what? S approach to 1, the singular point is this one, 0 times infinity. You know that this becomes 0, but this one, if your s approach to 1, goes to the infinity. Okay, but by cancel out that point, s approach to 1 becomes 1.5. Okay, that becomes this one, and s is 1, so e to the st. But this one is on the left side signal, so this is the result. And what about here? this one is a right side signal, so we have to calculate the residue value at that point. That's this one. So s plus 1 will cancel out. S approaches to 1, then this becomes okay, this s approaches to minus 1, then this one minus 2 and 1 over minus 2, and s approaches to minus 1 e to the minus t, and the right side is signal. So if region of convergence is given like that, then the inverse Laplace transform consisted, one is the left side signal and the other one is the right side signal. Some of them is the inverse Laplace transform of that. Now consider about xs like this one. We assume that the xt is causal. It means it is a right-sided signal. Okay, right-sided signal. xs has a double pole s equals 0, and s has a simple pole at s equals minus 1. So pole exists at 0 and minus 1 point, but this one is a double pole. Okay. To be causal, as I said, that it is a right-sided signal, and we have two different poles, but this one we will calculate first. It means that this is S domain. It has pole, and here is double pole, and it's a 0, and another pole is minus 1 point. So this one is a simple pole, and the region of convergence are defined the right side of the rightmost pole. At this moment, minus 1 and 0, the 0 is the rightmost pole, so region of convergence are defined in this way. So sigma should be positive. The maximum real pole is this one, the value of the pole. And to taking inverse Laplace transform, the path should be taken like this way. This is a straight line from bottom to top, and encircling all the pole. Okay, this is the closed path of that one. So this is straight line part, this one is a C1 part segment, and we need to calculate the residue value at the minus 1 and 0. So we will calculate at minus 1 first. Residue value can be found in this way in the simple pole. S approach to 1, and the s plus 1 times s1 will give the residue value. So at here that the s plus 1 is multiplied here, then there is s square is remained here, and s approach 1, then this value becomes the 1. So we don't care about this, but this value are equals to 1. From here to here, approach to 1. And s approach to 1, then it will give e to the st. Okay. Now consider about xs like this one. We assume that xt is causal. It means it is a right-sided signal. Okay, right-sided signal. xs has a double pole s equals 0, and s has a simple pole at s equals minus 1. So pole exists at 0 and minus 1 point, but this one is a double pole. Okay. To be causal, as I said, that it is a right-sided signal. And we have two different poles, but this one we will calculate first. It means that this is S domain. It has pole, and here is double pole, and it's a 0, and another pole is minus 1 point. So this one is a simple pole. And the region of convergence are defined the right side of the rightmost pole. At this moment, minus 1 and 0, the 0 is the rightmost pole, so region of convergence are defined in this way. So sigma should be positive. The maximum real pole is this one, the value of the pole. And to taking inverse Laplace transform, the path should be taken like this way. This is a straight line from bottom to top, and encircling all the pole. Okay, this is the closed path of that one. So this is straight line part, this one is a C1 part segment, and we need to calculate the residue value at the minus 1 and 0. So we will calculate at minus 1 first. Residue value at minus 1, we approach s to minus 1, s approaching to minus 1, and multiply the s plus 1 as xs. then xs will disappear. We replace s with -1, then it becomes the 1, and the s becomes the -1, so e to the minus t will come out like that. And as I talked to you that this one is a right side echelon to become the closure. And the second one we need to calculate at the 0 point, but in this case we have a double pole at the 0 point, and we have to find out the residue value for the double pole. Double pole case, we already know that the residue value in case of a double pole, we take the derivative and then apply the g0 value here. So to find out the double pole residue, we need to take the derivative first. This value s square is multiplied here, then this part is disappear, and we need to take d of ds, s approach to the 0, and if you multiply s square, then 1 over s plus 1 is here, and e to the st is like that. And taking derivative with respect to s, it will give these two values by taking derivative, and we approach s goes to the 0. Then if s goes to the 0, then this is 1 and this is equal 1, and it becomes a t. That's this part. Okay, and this one we take s as a 0 value, then this becomes the 1, and this is also 1, so it becomes the 1. And we also know that it is right side echelon. That's why inverse Laplace transform of this one becomes like that. Okay. Now consider the next example. At here, in this example, the HS has two complex poles. So here is HT is also causal. It means that it's a right side echelon, and it has two different poles at here. The pole located -1.5 plus minus j square root 2 over 2. So it looks like this one. This one is a two complex conjugate pole, and the real part is -1.5. So this is -1.5. And to become causal one, it should be right sided signal. Then the region of convergence should be this side, right side. Okay. Sigma should be greater than -1.5. Okay. So this is the region of convergence, like that. We need to take the contour integral in this side. So we have to evaluate the residue at these 2 points. S has the pole has two poles are given here. S1 and S2 are given like that. S1 defined the positive sign, and S2 is defined the negative signs. To find out the residue value at S equals to S1, then we multiply this value, then this part will drop out, and then the residue value are given like that. S is replaced by S1, and S1 minus S2 to the over e to the st, S1t, and the right side echelon. And the residue value at S2, we can do the same way, then it will become S2 minus S1 over e to the st and ut. And by summing up these two things, we can figure out this result. Then we can calculate the difference of the pole, and then we subtracting these two S1 minus, you know that S1 minus S2, S1 minus S2, real part will cancel out, and imaginary part will become j square root 2, like that. And S1 and S2 has you know that e to the S1t means that S has -1.5 e to the -1.5t times e to the j square root 3 over 2t. Okay, this one is e to the st. That's this part. And e to the s2t will be e to the -1.5t times e to the minus j square root 3 over 2t. Okay, then by subtracting this one, this e to the minus 1.5 t is common factor. That is this part. And then the imaginary part, e to the j square root 3 over 2t, and its conjugate remained here. By adding these two, by subtracting these two complex conjugate number, it will give 2j times sine value, sine over square root 3 over 2t. Okay. Then this j and j will cancel out. 2 over square root 3 and e to the minus t, and sine square root 3 over 2t, and the right side additional. This is the inverse Laplace transform of this one.